Officially at 5 after, so we'll get going. I'm assuming we'll have a few trickle in. So, those of you who are students, when you graduate and you go off to do really cool things, we occasionally call you up and say, "Can you come back and tell us about these really cool things that you're working on?" Bambi is one of these people. Fortunately, we didn't have to call very far.
Yeah.
It's on the street at University of Pittsburgh. But this is one of these nice things about being so close to University of Pittsburgh is there are opportunities to do really interesting things in rehabilitation and medicine. Today is more about rehabilitation, but I think this is a topic that I think more and more roboticists are going to start getting into, and you're going to see a lot more work in this area, especially as humanoid robotics gets closer to interaction with people as well. So, fire away.
Hi, I'm Bambi. I probably have the dubious distinction of being the only robotics graduate who's a faculty member who is in neither a computer science nor an engineering department. My home appointment is in the School of Health and Rehabilitation Sciences at the University of Pittsburgh in rehab science and technology. And my work concerns how robots interact with people who've had injury or disease of the brain. So I'm going to talk today. I kind of wanted to give an overview of a few different ways that robotics is used in this field. And I focus specifically on fine motor control, which is basically things you do with your hands, after neurological disease or injury. In a few different areas. First of all, using robots to assess disease, to measure how much of the disease essentially someone has, as well as why you would want to do that. Then the use of robotics for therapy to help people overcome motor deficits that can occur after brain injury. And then for those deficits that can't be addressed, the use of robots for permanent assistance of individuals with disability. So one of the things that I work on is looking at whether you can use those measurements that are possible with robotics, which are certainly more precise than any doctors typically take via clinical assessments. Can you use those to generate useful information for physicians about the state of someone's disease? When I first got into this area, the main question that occurred to me is, why would you want to know how advanced your Parkinson's disease was? Why would you want to diagnose it early if we don't have a cure? And the main reason is related to the development of new medications that can potentially slow the progress of the disease. It's hard to measure whether or not new medications work if you don't have any way to measure precisely the progress of the disease and how it changes or doesn't change over time. So we started using robotics to assess fine motor function, how people use their fingers in Parkinson's disease, because that's one of the first symptoms that people notice. In particular, I don't know if you've ever seen handwriting samples or anything from people with Parkinson's disease. They'll typically start on one side of the page and their handwriting looks normal, and they get smaller and smaller and smaller as they go across the page. So some people who are diagnosed at younger ages, the first person to notice is their secretary, because they notice that all of a sudden their writing is tiny and illegible. And when it hasn't been in the past, they've noticed changes there. We also wanted to look at the effect of trying to do multiple tasks at the same time on assessment. We've, of course, all accomplished multiple tasks at the same time all throughout the day. You're answering the phone while you're unloading the dishwasher, you're doing multiple things at the same time, and that type of multitasking is much harder for people with Parkinson's disease. And we wanted essentially to use the fact that it's much harder to make their motor deficits larger and easier for us to measure. So this was the first system that we started. There's no robot yet. The robot is coming. There's just some force sensors here. And the individual, in this case, Sujana Pradhan, who was a PhD student working on this, is grasping those little sensors and using how much she's pushing to track that wave that's shown on the screen. So we have a wave that looks like this. So they see it scrolling across the screen, and they're trying to make their little pink or purple line there match the black line in the center. And we tried a couple of different waves. This sine wave, where they know what's coming up, and it's the same thing for several minutes, so that they're able to predict what they're being asked to do. And also more of a pseudo-random wave, where they don't know, where they aren't shown what wave is coming in the future, and we measure how long it takes them to catch up with that wave. So they track these waves, and that's all well and good, but they do that for a minute, and then we make it more exciting by asking them to count down from 100 at the same time. So for the first minute, they're just tracking. For the second minute, they're counting down from 100 by 1. And for the third minute, they're continuing to track while counting down from 100 by 3, which is challenging. If you would like to try it, you're welcome to visit my laboratory and try it for yourself. It does definitely make the task harder. And so we looked at this with 30 individuals with Parkinson's disease and also 30 age-matched control subjects, so subjects that were the same age but as far as we know did not have Parkinson's disease. And your fine motor control does deteriorate with time, so it was important that these individuals be in the same age range as our subjects with Parkinson's disease. We tested both hands because Parkinson's typically affects the extremities asymmetrically, so people have one hand that exhibits more symptoms than another. And with both sine and pseudo-random waves. And we did ask everybody basically not to take their medication the morning they were tested. They brought it, they took it immediately afterwards. And we looked at a few different variables. If you've known anyone, seen Parkinson's disease or Michael J. Fox or anything on the news, the tremor that's most commonly associated with that, the symptom that's most commonly associated with that disease is tremor. And you can quantify, that's actually of a known frequency between 4 and 8 hertz. And so you can use the power spectral density to get a measurement of that tremor. We also looked at basically just the error in tracking, how far they were off the target wave. And in addition, the lag. So here, the blue is the pseudo-random wave that they were tracking, and the red is their response. And we were measuring how far they lagged behind the target wave. This is essentially quantifying a symptom of Parkinson's called bradykinesia, which means slowness of movement. They have a hard time starting to move and adjusting movement. So for instance, once they're walking, they're okay, but it's hard for them to get started walking, and it's hard for them to change direction. Also hard to get up from chairs, and you'll also see it in speech. There's a slowness to get started of the motor system involved in speech as well. So, in terms of our results, tremor actually wasn't that interesting, which surprised me at first because it's the symptom most commonly associated with Parkinson's disease if you see magazines and etc. But it turns out that only about half of the people with Parkinson's disease have it. So it turned out not to be as good of a measurement for us because it's not exhibited by every person with Parkinson's disease. What is associated with every person with Parkinson's disease is that bradykinesia. And we were able to pick that up well with the error and the lag. And what we found most interesting, I mean, we did see effects of what group people were in. That makes sense. The people in one group had Parkinson's disease. They were diagnosed with it. So one would only hope that we would notice some differences there. What we were particularly interested in is this significant interaction of group and task condition. That means that performing simultaneous tasks affected people with Parkinson's disease more than people without Parkinson's disease. So as you can see, this is just data for the one target wave, pseudorandom, and this is data for the other. And the controls are on the left side, and the people with Parkinson's disease are on the right side. And you can see that even for the controls over there on the far left, there's a slight upward trend in their error as we ask them to do a simultaneous task. So their performance deteriorates a little bit when we ask them to do two things at the same time. But that deterioration is much steeper for the individuals with Parkinson's disease. As they try to do two things at the same time, their motor performance, instead of getting a little bit worse, gets a whole lot worse. And we were hoping to use this to our advantage to make their motor problems larger and easier for us to quantify. And we saw pretty similar results in looking at the lag, how far behind the target wave they were, particularly in the pseudo-random trial. Their lags are on the order of a couple of seconds. It takes them a long time to catch up to that target wave. So we looked at differences between the groups because effectively that's what you do when you do human subject research. People expect you to look at those things and do analysis of variance. But we were more interested in looking at whether we could use our assessment to predict something that was clinically relevant. In essence, are we measuring whether they have Parkinson's disease or are we measuring something else? So we wanted to combine our data and look at it relative to a clinical assessment for Parkinson's disease. The one we chose is called the Unified Parkinson's Disease Rating Scale. There's nothing special about that particular scale except that it's a standard clinical assessment for Parkinson's disease. It's a form, it's about 40 questions long. Some of them you ask the patient and they self-report. Do you have problems swallowing food? Do you have problems with depression? Some of them the physician rates how well, when you ask them to move, to clench their fists and do it as fast as they can, are they slightly slow or a lot slow? Basically everything is rated from 0 to 4, so it's a pretty coarse measurement of the disease. And so we were trying to predict that with our data. And we used ridge and lasso regression, mostly because we don't have a ton of data. So we were doing cross-validation, but we were pretty much forced into leave one out cross-validation because we don't have 300 people with Parkinson's disease, and we can't get 300 people with Parkinson's disease. And so we were looking at how well we could predict that clinical score. And we were able to, the entire UPDRS, I believe the maximum score is 140. And we were able to get within 3 or 4 points of predicting their score. We were actually a little surprised that it worked that well because the UPDRS asks a lot of things that we don't even touch on, like do you have problems with depression? Do you have problems with dyskinesias, which are strange kind of extreme movements caused by the medication for Parkinson's disease? But this was helpful to us because it basically looked at, we can show that we had a people with range of Parkinson's disease scores, and we can measure a range of scores for them on our assessment, so that our assessment does essentially show a progression as people get clinically worse with Parkinson's disease. We also took a look at which variables we were actually using in this prediction, and most of those were the root mean square error, but we were particularly interested to see that most of the ones that were used in the prediction were those variables that were measured when people were doing 2 tasks at the same time. Those tended to correlate better with their clinical status than the ones where they were just force tracking. We also looked a little bit at classification, mostly only to see what variables were important. We don't have enough data to do this well at this point. We also have an added slight difficulty that we can't be 100% sure that none of our controls had Parkinson's disease. Above a certain age, if you just went door to door, that you would meet, I forget the percentage, but it's 5 or 10% of people study in California basically went door to door and looked at what percentage of people had undiagnosed Parkinson's disease. And that number is 5 or 10%. So we can't be totally sure that nobody in the control group didn't have Parkinson's disease. And there was also at least one person in the Parkinson's disease group who our physical therapist was relatively certain did not have Parkinson's disease. So we're not very sure that we have 100% ground truth here. There's some room for variability. So we can only classify about 85% of people, but we were mostly interested in what variables were important for that classification. In determining, as we moved forward with this, what things do we want to continue to measure? How do we potentially want to modify our assessment? And the tracking error did work out to be the best for us. The tremor integral, because not everyone exhibits it, doesn't seem to be a very useful variable for us. So in this study, we looked at 2 pretty different unrelated tasks. I mean, they're force tracking, and then they're doing something entirely different, the cognitive task of counting down from 100. And we were pleased to see that did cause greater motor deficits, as that had been our goal, and that we were able to measure something related to their clinical status. And after doing that, we wanted to determine, will any 2 tasks work, essentially? Is using 2 unrelated tasks different in some way from using 2 tasks that are related? So we also were measuring something that is not relevant to what these people have to perform in daily life. You never, well, maybe you do, you're a graduate student, but most people never sit down and track force for 3 minutes at a time and midway through decide to count down from 100 by 3. So we also wanted to look at modeling a task that's more similar to something that people do in daily life to see if that made a difference in our ability to assess this disease. So we looked at, we kept our force tracking task with counting because we wanted to compare to it. And we looked at another simultaneous task condition. So we asked people to track position while maintaining a certain grip force. So essentially, while I'm doing it with robots, they're doing something similar to moving an egg back and forth. So they have to exert enough force not to break it and not so much force that it drops. So that's essentially the functionally related task that we were looking at. We basically wanted to know whether doing two related motor tasks at the same time is different than doing two unrelated tasks at the same time. So this is where the robots come in. They're simulating the egg. So they're measuring force, they're measuring position as the person is performing position tracking. These robots don't measure force, so we had to attach little force sensors to them so that we could get force information as well. And so we shortened our force tracking task basically to deal with the fatigue issue. All of these people are older. They do have a neurological disease and they get tired easily. We needed to make sure that we were measuring motor signs of Parkinson's disease, not motor signs of getting tired. So we had them track for a little bit and then track while counting down from 100 by 3. And then we moved into the position tracking. We actually gave them about 30 seconds to just rest and then moved into the position tracking, where they're moving their hand horizontally back and forth. And they just position track for a minute, and then they do 30 seconds while maintaining grip force, first in a larger range and then in a smaller range. So this is what it looks like when you're position tracking. So you're moving your hand back and forth horizontally. We do horizontally because they can rest it on the table. It wouldn't be possible for these people to stand here like this and wave their arm back and forth for 2 or 3 minutes for us. And you see this box because my graphic skills are not so great and I couldn't make an egg. So you see your green box, and it's green if everything is happy. It's red if you're exerting too much force, and it's gray if you're not exerting enough force. Just so you know, people are given practice trials of this before we start, as well as a fairly extensive instruction process. So they do, in fact, know what's going on before we sit them down there and ask them to do this. Yes, Chris?
But they only see a slice, right? They don't see the preview of what's coming.
For this wave, they do see this preview of what's coming. So they see, I think this is a 12-second history of what's been passed. They're always at the center of the screen, and they see what's coming up. So this wave essentially scrolls downward as they're tracking. For the pseudo-random wave, the top of the screen is black. So they see that 12-second history, but they don't know what's coming up.
Okay.
Basically because we wanted to be able to look at it both ways. So this study has been quite recent, and so we've had 10 subjects with relatively early Parkinson's disease. We are taking people off medication. We are not going to do that for anybody whose balance is impaired when they are off medication. In addition, most of the drugs that are being developed to address Parkinson's disease are designed to slow its progress, so they're designed to be given early in the disease process. So we were most concerned with the ability. Yes, Chris?
So people who have Parkinson's that I know have to be fairly far along before they're taking any kind of medication because the diagnosis process is so lousy. Most clinicians, or the ones I've heard about, are very uncertain as Parkinson's. There's no blood test or anything. So it's they eyeball the behaviors. Oh yeah, it looks like Parkinson's. And given no one's sure, it takes a long time before they get around to saying, okay, let's take some drugs.
It is a hard thing to diagnose, and in fact, some ways, the way that some physicians diagnose is basically to give them dopamine. If dopamine makes the symptoms better, then you have Parkinson's disease. If it doesn't make the symptoms better, then you don't have Parkinson's disease. We do have a small caveat in that we were recruiting through a registry maintained by the Movement Disorders Clinic at UPMC. So we had people who had been to the Movement Disorders Clinic, and those are more likely to be diagnosed early than people who are diagnosed by their primary care physician, because they're going to the neurologist who specializes in that disorder. So we probably do have an earlier group than you would typically find if you recruited in general. We did go through some support groups as well, so we do have some people who are diagnosed at a later date. And people seem to vary greatly in how quickly the disease progresses. Some people are diagnosed, and for 10, 12 years, their symptoms don't seem to change very much. Some people are diagnosed and within a year their symptoms have become much, much worse. So there's a lot of variances there. We have a good bit of variance. Those people who were down at the low UPDRS scores, that's basically you can barely, even off medication, can barely tell them from someone who doesn't have Parkinson's disease. So we saw basically the same results for force tracking. We checked that only to make sure, because that would be, we did want to make sure we could replicate that we hadn't misinterpreted our original data. But interestingly, we didn't see an effect of performing a simultaneous task when somebody was position tracking. They basically were able to do the position tracking task just as well while maintaining their grip force, whereas they weren't able to force track while performing a simultaneous cognitive task. Now, we only analyzed this data last week. I don't have an excellent explanation for you as to why that is, though I'm happy if anyone has any ideas about what might cause that. I'm more than happy to entertain suggestions. I have a couple of thoughts. The first being, it is possible that force tracking is just harder because we don't do it every day. And so they had to devote more attentional resources to that, and the effect of that caused it to be harder to do a simultaneous task at the same time. The other would be that if you're doing, that they have essentially been training themselves in daily life to continue to be able to perform simultaneous motor tasks as well. And if you practice something, you will maintain that skill better than if you don't, even in the case of Parkinson's disease. In our earliest experiments, we actually had 2 people with Parkinson's disease who performed just as well as our controls. Turns out that those were the 2 people who regularly played musical instruments. You can maintain those skills if you practice hard enough. Now, they will eventually deteriorate. But there is a significant effect of training, even in the case of degenerative disorders. Yes?
How far do you have to move your fingers to change the force?
To change the force, when it was just the force sensors in the first experiment, not at all. Those were basically measuring it isometrically. In the robot, because of the way you have to do the haptic interaction, they're moving a small amount, but it's quite small. Only a couple of millimeters. So you don't have to have a lot of movement there for the force.
Because otherwise you would think maybe they're just fixing their fingers in one position. And as long as they don't vary the distance between their fingers, they're not varying the force. Right.
They do seem to be varying in that they are making errors in the force tracking. And in fact, if I sat you down, and presumably you don't have Parkinson's, but if I sat you down, you would make errors too. So we did choose those that even controls couldn't perform perfectly.
Although I am aging.
Well, if you'd like, you can come down. We will test you. So we are looking into that as to what's different about performing these 2 motor tasks as to performing these two cognitive tasks instead. It wasn't necessarily bad news for me that the position tracking wasn't better. I was interested in looking at a functionally related task, but not needing the robots has serious advantages in that the system is portable without them, and people with Parkinson's would much rather you brought your system to their house to test them than to drag them off medication into your laboratory to test them. So if one of the reasons that we did this was to find out, do we get anything from that functionally related task that we can't get without it? Because if we can do everything that we need without it, if it doesn't gain any additional information, then we can make the system simpler and more portable. So assessment is, in some senses, an easier task in that people are typically, you don't assess them in their homes, or at least they come into clinics to be assessed. So there are personnel there to help. And it's the tools that we were looking at would be primarily of interest in research to measure the effects of new medications in the cases of things like clinical trials. But we'd also like to use robotics to actually not only measure deficits you may have in your motor system, but also to help decrease those deficits in individuals. And I'm certainly far from the only person who does this. If you've seen one rehabilitation robot, this is probably him. This is the InMotion 2, which was originally the MIT Manus, which changed names when it became commercially available. And they built the first one about 1993, 1994, and started testing. And they've worked with several hundred stroke patients. And people have worked with other different types of robots for therapy. And overall, the general feeling at this point is that working with a robot is effectively the same as doing a similar amount of regular therapy, which at first sounds a little bit depressing, except that people currently don't get enough regular therapy. You have a stroke, you're sent to rehabilitation for a short period of time, basically until you can be charged to your home, but there's not a lot of follow-up for months afterwards. People are capable of making motor improvements years after stroke, but almost no one gets rehabilitation then. So being able to change some of those motor parameters with robotic systems, particularly simpler systems that people could use in their homes, would have a serious advantage in that it would simply increase the total amount of therapy that people are able to get. And the results are very strong. The more therapy you get, the better off the better your outcome is going to be. It takes a lot of repetitive movements to persuade your brain to make changes after stroke. So in general, in most of these studies, there arises the question as to what the robot should ask the person to do. And the logical and typical way to decide this is you have the person come into your laboratory, you sit them down, you ask them to move with the robot, you measure what they do, and then you ask them to do that again. The problem with this is that is not necessarily related in any way to what that person is actually capable of doing. After stroke, you form pretty strong habits of not using an arm because in therapy and in your daily life, you have to use the other arm to do everything. And that is very true in the first stages after stroke. After 6 or 7 months, after your brain has had a chance to reorganize, you're actually capable of doing more than that with the arm that is paralyzed. But you have learned a habit of not using it. And it is very difficult to overcome that habit. And I say arms because while stroke affects legs as well, you can't walk with just one. And so it's less likely that people are going to form that habit of non-use because you need 2 legs to walk. You can function pretty well, though not optimally, with just one arm. So you don't want to necessarily base what you're asking somebody to do on the first thing that they do when they sit down at your robot because you need to move them beyond those habits of not using that arm. And I did some of this here as my dissertation work. Looking at whether you can persuade people to move farther. So if they're playing a little game of hangman and you make it harder to get to the ends of the alphabet, can you get them to move farther than they did when they came into the room and sat down? And this was able to influence people's performance. But there were a lot of unanswered questions there. In particular, it doesn't matter if they know that you're changing things. You could think, you can make it obvious to them that change is occurring, that you are making it harder to play the game, or you can avoid having them know this. And it wasn't clear which of those would be most useful for individuals with stroke. In addition, people were surprisingly willing to go along with this change, so much so that we never figured out at what point they would stop and say, no more. They were always given that option and had big bold print on the bottom of the computer screen. If the game becomes too difficult to play, you may ask the experimenter to make it easier. But no one ever took us up on that. We had based what we were asking them to do on the opinion of an occupational therapist, and who is an excellent occupational therapist. I say this not to disparage her, as she's really very good, as to what she had told us to ask them to do. She had said if they go through their whole range of motion, what they'll be able to hit consistently is 80% of that, if you're going to do this therapy over an hour. People were in fact capable of hitting way over 80% of that on a regular basis. So we didn't find out how far they could go because we didn't ask them to go quite far enough, because we started at 80% and then made it more difficult from there, as opposed to starting at 100% and then making it more difficult. So we wanted to know 2 things. First of all, whether we could start at their maximum and go further, and also does it matter whether or not people know that essentially the game is getting harder. So I first looked at whether it mattered whether or not you made the game harder. And I tested this in people who hadn't had strokes because they're much easier to recruit. So what they're doing is they're grabbing the endpoint of the robot and they're trying to move as far as possible on every trial, because I needed a task at which there was no upper limit. I needed there not to be a ceiling effect of how well you could possibly do. So they're basically experiencing a viscous force and trying to move as far as they can in about half a second. And they're doing this in a few different conditions. First of all, with no visual feedback whatsoever. Second of all, given a goal that's a pretty difficult goal. It was their initial performance plus 5%, I believe, because there is evidence in psychology that simply having a goal will improve your performance as well. So it's not they had a goal, then the goal changed, but they didn't know it was changing, and the goal changed, and they did know it was changing. So what they saw were some boxes. So if you were doing this experiment, you are the green box, and the white box here is your goal. So you're trying to make the entire white box green. And to make good and sure you knew when the goal was changing, in the explicitly changing condition, the change is purple, so that I will make sure you notice it. So when you see the box have an extra increment here, you have to make your green box fill the whole area there. I did in the condition where the goal changed implicitly. The size of the box here stayed the same, but you had to move further in order to fill the whole white box. And in addition, because prior experience had told me that how you instruct people affects how they will perform the task, we had two groups of people that got different instructions. The vision group was given kind of the typical instructions. The box on the white screen is your goal. Try to fill the entire white box. These instructions were in fact videotaped so we could make sure that everybody got the same directions. In the kinesthesis group, they were really hammered into their heads that their only goal was to move their arm as far as possible on each trial. So they were basically instructed to attend only to their arm and rather than the visual feedback. So for the people who were using in the vision group, we saw that their performance was much better when those goals changed. And it didn't seem to matter whether it changed explicitly or implicitly. Their performance with a goal and without visual feedback were pretty similar and much lower, even though, as I say, that goal was set to be pretty difficult. They had already practiced the task, so they had practiced the task enough that they weren't still learning, essentially. And we took their performance then, and the goal actually was 5% above that. Now, if you really hammer it into their heads that they're supposed to pay attention only to their arm, you can eliminate that fact. In this condition, people were attending just to how far they moved their arm, and their performance was the same in all conditions. We did that because humans are strongly visual creatures. We almost always rely on vision. Because statistically, it's the sense we measure best. So our brains actually kind of combine all our sources of input optimally and rely on vision because as you walk along, it is more likely to be the sense giving you the right result. So we did this because we weren't actually sure that we could turn that off at all. We expected that that no matter what you told them to attend to, they would still use the visual feedback. But we would expect that in a paradigm designed for robotic rehabilitation, that people would be attending to the feedback, particularly as one of the primary goals in robotic rehabilitation is to make the repetitive exercise more like a game, to make sure that people do it. Therapy will certainly make you lots better if you perform those repetitive movements every day. The main problem that therapists see is that people do not want to perform those repetitive movements every day because it is boring. And so they send them home with their home exercises, and people don't do their home exercises, and so they don't obtain as good an outcome as they could. So we then wanted to basically make sure that the same was true for individuals with stroke. We didn't use the same task because it was too difficult for people with stroke to accomplish. Instead, we used this device, which is called the Intellistretch. It's a very simple device made by a company, Rehabilitation, in Chicago, that allows an individual to make movements of a single joint. You can change which joint it is. We used it for the wrist and the elbow. And it measures their position, and it can provide haptic feedback. In fact, here we were just using it to measure their position. So we had two questions. Rehab Tech wanted to know whether the measurements they make with their device are the same as you would measure with a goniometer, which is basically a protractor that you would use to measure that range of motion. And we wanted to know whether using distortion changed their performance. So it was the same type of setup in that they were asked to execute their range of motion, and I'm going to demonstrate with the elbow. And we customized this display to each person because we had radically different ranges of motion because people had different severities of stroke. And we started at their range of motion and then asked them to extend that basically by 4 degrees, then 8 degrees, then 12 degrees, then 16 degrees. So they're being asked to move substantially farther by the end of this. They all did start with limited range of motion, so 16 degrees wasn't going to put them at the limits of their bones. And for the elbow, this worked pretty well. They actually did move 5 or 10 degrees further as we asked them to do more than they did at the beginning, and then they did in goniometry. And we see the same trend in the wrist, though we didn't see that as being statistically significant for the wrist. We see a lot of variability here, which we think is due to some people got tired after about this many trials, and so we had some fatigue effects towards the end. But we did see a significant effect of that distortion at the elbow. In addition, we're missing one person wasn't included in the wrist because they couldn't move their wrist at all. And we did see that that their performance was pretty constant on trials with no distortion. We don't have those trials for every subject because using a new system with stroke subjects is exciting. And for the first 7, we were just really for the first few, we were really struggling with the system, and we weren't able to take as much data as we were for the later subjects. Intriguingly, you would expect that if you measure the range of motion automatically and you measure it with a protractor, that you would get the same number. In fact, you don't. You get a correlated number, which is good. You can predict the number you would get with the protractor, but that slope is not 1 as you would expect. We suspect that is because in fact, the machine overestimates for some people and underestimates for others. So it's like the machine we would expect, the machine has some resistance. So I would expect for people who are weaker that the range of motion we measure with the machine is going to be slightly less. That is true. For some people, on the other hand, we measure a larger range of motion with the machine than with the protractor. And we're not entirely sure why that is, but a number of people with stroke do experience spasticity, which is essentially like contractions in their muscles. And the machine does give some stability that may be countering a portion of that. So it may be essentially giving a boost to some of our subjects. So we were able to use this goal change to affect their performance, but this was just a single session task. So it was a proof of concept to make sure that we could do this in people with stroke, starting from their maximum and going forward. And we now want to do this in home therapy. But we don't want to use the Rehab Tech system because you can only do one joint. So we're going to be using this glove. If anybody's used the Cyberglove, it's basically a cheap Cyberglove. It has fewer sensors, but it's the same type of thing. So it's a data glove marketed by a company called Intellistretch, and we're going to make some software for it that we're going to deploy in homes in Pittsburgh in 2012 because we have to spend 2011 making sure that the measurements we take with the device bear some vague resemblance to what people's hands are actually doing. And so we're going to use this to look at basically some days in therapy, people will have the distortion or the goal change. It doesn't seem to matter whether we tell them about it or not. And some days they won't. And we're going to look basically at how hard they work on each day. And in addition, how long they'll be given the choice basically of how long to exercise, and that's an important variable for us, because if they perform better with the distortion but they quit sooner, that's not good for us. We want people to continue to exercise with this device, and we want to make the exercise as entertaining as possible to maximize the portion of time that people are willing to do it. Finally, the last thing I wanted to touch on today is robotics for assisting individuals. And a number of these robots have been built. This is a wheelchair arm that's marketed by a company that's in the Netherlands. But as you can see, well, maybe you can't see in the picture, she's using a keypad over there to control it. If you have motor problems large enough that you need a robot to assist you, it is likely that your motor control is not really up to the task of operating that robot via a keypad. And I've used this robot. It's quite slow. It's very slow to make it do what you want it to. And there's also the obvious problem that you're moving that joystick or that keypad in 2 dimensions, and your robot is moving in 3 dimensions. So it also requires substantial cognitive effort to switch those modes and control the 3-dimensional endpoint of the robot. And Chris has seen this work before, so he can rest over there and take a break. We're looking at different ways for people to interact with these robots to make it a little faster and a little easier to accomplish that interaction. So this robot is wearing a little outfit that is basically a giant switch, so that we know when you touch the robot. So when you're touching the robot, it moves as though it was weightless, and otherwise it stays fixed in position. So our concept here is that somebody is using this robot basically as an individual would use an upper extremity prosthesis. If you've ever seen anybody wearing a hook or seen anybody using a hook in movies, they're basically only holding on to the object. They're not manipulating it. In prosthetics, they're basically called portable vices. It's a tool just to stabilize an object. And that's what we were looking at using this robot to do for our target group of individuals with hemiplegia due to stroke. So one side that's completely paralyzed that they can't use to perform manual tasks. So I have a video. Oh, good, that's even playing. Of some example tasks that we're going to be looking at. And you'll see her, she's opening and closing the hook with the keyboard. That actually can be done with voice control now. But I can't figure out where my undergraduate put that video. So we still have this one. And so you can use the robot to stabilize that device as you're doing tasks that we would typically do with 2 hands. Such as stabilizing an object while you're stirring, or this was one that our OT says is a real problem. People with stroke can put a glove on their bad hand pretty easily. It's putting a glove on their good hand that proves quite problematic because they can't hold on to it with their bad hand. So there's no way to keep it in place while they put their unimpaired hand into it. We were also looking at the use of this robot to provide a little extra strength in lifting heavy objects from the floor, for example, while unloading your groceries or performing a task like that. Wow, this is quite a long video. I didn't realize it was quite this lengthy. Mm-hmm. And so we'll be testing this out with a set of potential users. Basically because we wanted to see how comfortable people are interacting with the robot in this way before we get too far down this path and discover that people with stroke hate it and would never ever want to use it. So we'll be having some initial test users in over the winter. And they're going to try out a series of tasks. We've outlined a series of tasks. Some of them are in this video, and I think we have some others that they're going to go through to make sure that they have experience interacting with the robot. And then ask them their opinions and what needs to be improved. And we'll certainly see substantial variation there because, for instance, the voice commands may work well for some people and not so well for individuals whose speech was affected by the stroke. So we are expecting to need a few different ways to interact with this robot in order to let people interact in a way that's most comfortable for them. So I think that was, and I'm finishing relatively on time. I think that was everything that I had wanted to talk about. A lot of my work has been in figuring out how people and their brains work, in addition to, because the first time that anybody sits down in a new experiment, something always happens that you didn't expect. People, particularly people after they've had a neurological issue, can behave in very unpredictable ways with your robot. And so making things that are robust and are measuring what you meant to measure and not some other variable is quite challenging, but I think it is a very rewarding area to work in that you do get to interact with individuals, and most of them are really excited to participate in research, even if they know that that a cure or an improvement is a long way off. They typically want to be involved in that, so that if things aren't better for them, at least they'll be better for people down the road. I have to remember to acknowledge the people who fund me, as well as the students who did some of this work, even Brandon, who hid his videos somewhere and won't tell me where they are. And I think that was everything, except for anybody who knew me when I was here, when I had a tiny baby. I have a much bigger one now.
We have time for questions?
Well, yeah. Interesting work, a lot of experiments, interesting experiment here. Yeah, robot for rehabilitation and therapy, fine, we have the application. But I am not sure how your robot actually was used for predicting the Parkinson's disease, for example. You gave the example that the robot is handling the ache, right? Now, when the robot is handling the ache, if you are trying to take the force feedback, and if you are trying to tell, like, this is the ideal one. It's very difficult. Anybody will fail in the test, for example. That will not be an ideal one because the robot has different structure and it is moving with different velocity. So
And
a person, a subject is moving with the egg and a robot is moving with the egg. To try to compare how effective it will be at normal.
certainly, it is not exactly the same as a real-world task. And our goal in that project was mostly to see if we can augment clinicians' analyses of how people function. They do rate those, but many of those scales are relatively crude. They are useful in the clinic. They are less useful for clinical trials when you don't want to wait 3 years on a new medication to find out how much someone is changing. So our goal was to be able to use a level of increased precision to hopefully shorten the time that it takes to tell whether medication is making a difference. And we were interested in, so to do that, we essentially had to model a task. Because, well, I suppose you could have thought about doing it with motion capture, but for an assessment, we needed everybody to accomplish the same structured task in the same way. And so we were mostly interested in that, in measuring something that was more functionally relevant to see if it gave us more information. Certainly, it is not a one-to-one analog of how you would accomplish a daily task.
And the second observation was how your support vector machine is used. What type of data you are handling with your support vector machine?
Oh, that was, so what we were working with was the tremor integral and the root mean square error and the lag, and we divided those up by the time period, so separately for when they were tracking versus when they were doing the simultaneous tasks
so that
as well.
Capturing, I think you can do by regression analysis also. Is it really require support vector machine to?
The reason I went with support vector machines is because they rely on those people near the boundary. And I didn't want to bias it too much with people whose Parkinson's disease was more advanced. So certainly, and that was, I am not an expert on classification, so there may well be better ways of going about that. But that was the reason I chose support vector machines, was because I wanted it to rely more on either controls who were closer to having Parkinson's and Parkinsons who were closer to being controls. I was worried with some of the other methods that those people whose Parkinson's was more advanced would have a large effect. Yes, Matt.
I was interested in seeing that people are using a traditional-looking prosthetic hook as a tool. Because just lately I've been trying to figure out why is it that, I mean, if you go and look at all the manipulation tools that people build, pliers, clamps, et cetera, you know, the pickup tools that you buy to extend your reach, that none of them look like prosthetic hooks. But if you design something or you buy something to actually, you know, as a prosthetic device, of course, it often looks like a prosthetic hook. And here's an example of somebody that's using something that's a tool, but it is designed to look like a prosthetic hook. And I'm just wondering if, from this experience or from the whole enterprise, if you can tell us why do none of our manipulation tools, except the prosthetic hook, have that kind of shape to the...
Well, now a lot of the manipulation tools, like the wrenches that you're referring to, prosthetic hooks are designed where you can open it as well by pulling on that lever with the cable, which most of those manipulation tools you're referring to, like the wrench, don't. You don't have essentially that active motion. They're just passive. And you can, there's actually a company that basically will sell those tools to fit onto your prosthesis for people as well. But so if, say, we were using the tool, we would either have to be harnessed with the cable to open and close the hook, because otherwise it's just hook-shaped, which wouldn't be so useful. What's useful from the point of view of prosthetics is that you have that hook shape and you can open it. I can't really do it, but you can open it like that to be able to pinch objects between it as well. And that would be hard to model for, I mean, potentially, definitely not for a robot using it, but for a human using that tool who probably is not going to want to wear the harness necessary to open it. But I don't know if that answers the question. Because you would have to open it. Yeah.
Just a question for the therapy. One of your concerns is getting people to do it enough. Have you looked into using your devices to replace one or two of the degrees of freedom in a standard computer input so that you can just run commercial software? Set it up so that you can play wild by flexing your arms and not have people spending too much time.
Well, and some people have looked at using the Wii for rehabilitation. I think the main problem with that is that it's too easy to cheat by not moving. Like, it's perfectly possible to play the game well without moving that much. And
Just adjust your games so that you can't get useful control inputs without large.
And people have been, I've been more interested in fine motor control, in which case you do need essentially more degrees of freedom. But the device we're going to use does hook directly into a USB. I'm working with the one problem that you have to be a little bit careful with is that you have kind of a twofold problem. You want it to be entertaining enough that people want to play, but you want to train a motion that they're going to use. You need to make sure that it transfers to daily life. And there's actually quite a vigorous debate in robotic rehabilitation, from people who do want to play just any game and make it as fun as possible, to people who are trying to model things like supermarket shopping, trying to increase that transfer. And currently we don't know where that happy medium is, and fun enough to keep people playing, but relevant enough to make sure that they do use that in their home as well.
You got Call of Duty shopping center.
Okay. Okay. My rehab is not going to have Call of Duty shopping center. Yeah.
Have you looked at the long-term assessment of this more detailed measure of how, something like Parkinson's disease progresses?
We actually are trying, and we have IRB approval. We've just been waiting for the 6-month. We have 6-month follow-ups for a couple of people, but not enough yet to assess the data. We tried to follow. What we did learn from their first experiment is that you should need to follow up every 3 months or every 6 months. We tried to follow up that first group of 30 at 12 months, and could only get 1 or 2. At that point, a number of people's disease had progressed to the point where they couldn't come off medication, or they had a spouse who had a health problem, or we simply couldn't find them. And that population, there's a lot of transitions that can make it difficult to follow up. So we're trying, with our later people, we are trying to get that information. But you really need to call them at least every 3 months to make sure you haven't lost them.
All right, thank you very much.
Thank you.